Thank you very much, Audron. And first of all, I want to thank to the organizers of the ICCP Journal Club to allow me to present you what we are doing in the framework of the research infrastructure Jagos and in our recent work, particularly on the investigation of contrails and the formation of contrails within cirrus clouds. This is a new field, and we are actually, and the results here are coming from a paper we have actually submitted and which is now under review, and we hopefully get it out quickly. So the talk will deal with what we found out about most contrails, that they form within cirrus clouds, and what is the climate impact of that. This is a hot topic in a specific area, and which I will introduce to you. And to understand the whole field around that, I want to start with the general look at the aviation climate impacts, because this is the field which defines the whole environment this work needs to be viewed at. So this is quite famous, and a figure from David Lee's paper in 2021, which summarizes the different terms of the global aviation effective radiative forcing. And I don't want to go into detail here. I just want to point to the top row where you see the contrail cirrus in high humidity regions. These are these man-made human clouds forming from the exhaust of contrails under certain conditions, and you see that it has a considerably high contribution to the overall effective radiative forcing, which is shown at the very bottom of the figure, and the range of uncertainties is very high here. And this paper is from 2021, but the situation has not really changed by now. So we can summarize in a way that we can say that these so-called non-CO2 climate effects of aviation, which refers to all impacts of aviation on the climate except the direct effect of CO2 emissions, they account for 2/3 of the overall aviation's climate impact. That means it's more than only the CO2 effects we need to look at. And from these so-called non-CO2 effects of aviation, contrail cirrus, which is here at the top, it really dominates the non-CO2 warming effect. And the impact of aviation on atmospheric aerosol, that's largely unknown here. That's the other big area of uncertainty. But we want to focus here on the contrail cirrus and help to improve a bit the knowledge on that to help better quantify the radiative impacts from this type of clouds. So let me start first with a quick look at the contrails themselves. So what are they and how do they interact with climate? All of you know these linear contrails which form behind aircraft in the plume, in the hot exhaust plume, mixing with the cold surrounding air, and under given conditions predicted by thermodynamics, these ice crystals form in the wake, and these are the typical line-shaped contrails all of you know. Under given conditions, when the air is cold and humid enough, these contrails may live long enough to develop into so-called contrail cirrus. That means they lose their linear shape and may spread out into a larger aerial cloud. And that effect or that evolution needs the supersaturation with respect to ice, and that happens within tens of minutes. If the contrail on the contrail cirrus lives even longer, then this persistent contrail, which is here in the middle, may develop into a contrail cirrus that spreads out into a cloud, losing really the linear shape. And again, ice supersaturation is required, and the lifetime of that contrail cirrus depends on the temperature and the ice supersaturation and the winds, of course. And it's really hard to predict. The climate impacts of these type of clouds are twofold, as you see in the bottom figure. So on this solar spectrum, they reflect incoming solar radiation during daytime. That means they have an element which is daytime cooling as an effect. And on the other side, in the infrared spectral regions, these are high ice clouds, and their overall impact is an infrared radiation warming because they absorb the terrestrial radiation coming from the surface of the Earth. That means overall, the net effect is a warming effect with a daytime cooling element and a daytime and nighttime warming element. Now, if we look at the evolution of clouds, you see another nice picture from the sky over Jülich, where you see the various stages of the contrail evolution. So we have the young contrails here, which is the clear linear shape. You see, even if this is evolving in blue sky, the radiative impact or effect is really small because simply of the small area covered here. If it lives long enough to develop in a long-living or persistent contrail, as you see below, it spreads and covers a larger area and evolves into contrail cirrus, which may become embedded into subvisible clouds in the background. Still, the contrast to the otherwise blue sky is quite large, and we expect from this type of cloud a significant warming effect. If we look at the lower part of the figure, you see contrail cirrus, which have further developed in already cloudy skies. You see here that the contrast between the contrails and the surrounding cloud is not as large anymore, and the overall optical depths and thus the radiative impact is determined by the cirrus clouds. We have a low contrast to sky without contrail cirrus, and we expect from this an only minor warming case. This is only very qualitative, but I think it illustrates quite nicely the effects of what we expect. Now, I mentioned that we require ice supersaturation. That is a common understanding. That means relative humidity with respect to ice is 100% or higher, that these contrail cirrus can exist for long enough timescales to develop a radiative impact. However, in a recent analysis from the HALO ML Cirrus campaign of a European group on the HALO research aircraft of DLR, Lee et al. Found out that the majority of contrail cirrus is found in slight subsaturation. You see in the center plot the distribution function of relative humidity over ice for natural cirrus in black, for contrail cirrus in red, and for contrail cirrus validated by additional measurements of aircraft emission elements to kind of justify the selection. And for both contrail cirrus ensembles, you see that they have a peak near 90%. That means contrail cirrus may already exist at slight subsaturation with a relative humidity over ice above 90%. And we need to consider that when we speak about lifetime and speak about potential areas in the sky which can develop this kind of climate impact of aviation by contrail cirrus. So let's now have a conceptual look on the impact of contrails in clouds on this conceptual figure you see here. If we start to the bottom, to the black part in the contrail index 0, that's the case where we have only a short-lived contrail, so we expect no development and no climate impact here because the contrail will dissolve quickly enough without becoming radiatively relevant. If we start here in clear sky forming a contrail, let's CO1, contrail 1, it might develop under given conditions into a contrail cirrus 1, which is then already visible, as you saw the nice figure at the beginning. So we have the transition from clear sky to visible, and this is where we increase the contrast to the clear sky without the contrail, and from that we expect a warming effect. A similar thing may happen if the contrail is forming inside a subvisible cloud and then evolves into a contrail cirrus embedded in a visible cloud. Again here, the contrast to the sky scene without the contrail is large, and from that a net warming effect is not only expected, this is also justified by satellite observations in cases where they investigated radiative effects from clear sky and contrails in clear sky and contrails in clouds. So we know that this will go in this direction. However, if we have a contrail forming in an already existing visible cloud, it may shift the contrail cirrus may move into a thick cloud already, And that can have ambiguous effects, either with a minor warming, or if we go to case 4, when we start at an already thick cloud, adding another contrail may shift the whole cloud thickness to a range where we move from minor warming to cooling effects. That means overall, we can distinguish here between the case 0 with no contrail, we expect no climate impact. Cases 1 and 2, there is contrail Cirrus net warming expected from that, net warming climate category. And cases 3 and 4, they include both minor warming and cooling. And this is what we now categorize as an ambiguous climate impact. And so from that, you see how important it is where the contrail Cirrus exists then, because this has a major impact on the resulting climate effect. For all of that, detailed radiative transfer calculations are missing. And this is really one thing which we need to know. And our study now aims to identify the regions where these various cases 1, 2, 3, and 4 occur. So the open questions here on that topic is, as I said, which fraction of contrail Cirrus exist in clear sky, subvisible clouds, and visible to optically thick clouds to determine potential climate impacts, and what is their radiative impact of that? These are really the open questions which need to be tackled. Our contribution to, let's say, narrow the knowledge gap on that topic comes from a specific research infrastructure we are running here in Europe, and that consists of actually 10 passenger aircraft equipped with a suite of instruments operated by 8 airlines globally. And these aircraft measure routinely on each flight a set of greenhouse gases, reactive gases, water vapor, aerosol, and clouds. And these continuous measurements build up a database which are available to the scientific community by open access. And we use this data to investigate our research topic on the contrails forming inside clouds and outside clouds. The water vapor measurements on this passenger aircraft are performed by a capacitive hygrometer, which is mounted inside such a traditional rose mount inlet. It's a similar sensor which is used for radio sondes. We know from in-flight comparisons that it has a precision of about 5% relative humidity, so it's good for higher humidities. We have a detection limit which allows not to sample really dry air. However, the advantage is there is no sampling line and no pumps required to that instrument, which makes it suitable for operation on passenger aircraft. We have an increased response time when it gets cold because the sensor works with the absorption of water vapor into a membrane, changing the capacity of this sensor. And at low temperatures below 40 degrees centigrade, we may have a response time in the order of minutes. When it's warmer, it's the order of seconds. And we have the limitation that we do not detect dry air in the stratosphere. That means this analysis is restricted. We focus on clouds anyway to the tropopause and below. So the water vapor information comes from the in situ observations of the relative humidity, and we added to that the ERA 5 cloud ice water content as a separator or categorizing quantity to separate clear sky from thin clouds and thick clouds. And these thresholds were determined from other knowledge. So for clear sky, we went for a threshold of 0.001 parts per million by volume. And this is justified by observations from the Nixe cups and from the fish instruments where the total water and gas phase water has been measured. And we could show that, Martina in one of her work could show that already at a 1 ppm cloud ice water content, this is resolvable. So then we have already clouds. And the threshold between thin clouds and thick clouds was determined from the assumption of an optical visibility threshold for 500-meter thick clouds. So that's a calculation based on the typical values included in ERA 5 to transfer the cloud ice water content into optical thickness. This altogether gives the database we are working on. And the data analysis strategy is that we start with a distribution of relative humidity over ice from in situ observations, not from models. Here it's really in situ observations. We check the fulfillment of Schmidt-Appelman criteria and use the in situ measured temperature, so the real temperature, to decide whether the air mass promotes formation of contrails or not. We take the Cirrus cloud coverage from ERA 5 cloud ice water content, which takes also cloud observations by assimilation of satellite radiance measurements. So that's a quite good representation. And we use the cloud ice water content threshold for the distinction between areas covered by clear sky, subvisible or visible clouds. So this is the strategy we started with. The area or we worked on the data set is shown here. So we are focusing on two regions. The most important region is in the northern mid-latitudes, ranging from Eastern North America to Europe, covering the North Atlantic Flight Corridor. With these three regions in the presentations here, we show this all as a whole, but we have also information or variability between regions over ocean and region over land. And we took as another region for reference the area over Southeast Asia, where we have also a lot of observations and dense air traffic, and these are the two most densest airspaces worldwide. The period covered the data from 2014 to 2021 with the temperatures below 235 kelvins to exclude liquid clouds and above 8.1 kilometers altitude. And we also excluded very dry air to focus on the regions below the thermal tropopause and focus on the upper troposphere where we really see the clouds. Now, just to give you an idea, we have in this area of the northern mid-latitudes, we have data from around 10 million flight kilometers, over Southeast Asia, 6 million flight kilometers. So this is really a huge data set, which provides some statistical robustness. The first result from this analysis, you see here the summary of the analysis of the fraction of air masses. That means we were calculating how many of the air masses do not promote contrail formation, how many of them have Schmidt-Appelman criteria fulfilled, but the threshold relative humidity over ice is below either 90% or 100%. So they are far away from saturation, so that these contrails will definitely be short-lived. And the third category is Schmidt-Appelman criteria fulfilled, and the thresholds exceeded either for contrail Cirrus existence in slight subsaturation or in saturation, in ice saturation. And you see at the first glance that in this, for the northern mid-latitudes, the air masses which do not promote contrail formation, they are really almost negligible. The biggest part, of course, is the air masses which promote the formation of short-lived contrails. They have not really a climate effect. And the long-lived contrails, which can develop a radiative impact, they can reach up to between 27% and almost 20%, depending on the threshold. But you see here quite clearly that by far the largest part is found inside pre-existing clouds. So the long-lived contrails, as a summary here, if we look only at the case with a 90% threshold, we found about 4% in clear sky, in cloud 24%, and in total it's 27% of contrails we see here. So that's basically this bar here, sorry. That shows the importance of the contrail Cirrus developing inside clouds. If we look now as a reference, not at all data, but only at those data which already fulfill the Schmidt-Appelman criteria, then we see that 30% of the contrails, of all contrails which can form in clear sky, 41% form in subvisible cirrus, and 46% in visible cirrus. So you see again here the high importance of contrails in these different types of clouds, which needs to be taken into account. If we put that now into together in a concept here, we sorted them according to the cases where we don't see persistent contrails. These are considered or categorized as no impact. The cases where we see contrails forming invisible cirrus, please recall that this may result in a minor warming or already in a cooling, depending on the conditions of the pre-existing cirrus. This category is defined as ambiguous because it can be minor warming or cooling. And we have a case where contrail cirrus forms in clear sky or subvisible cirrus, and these are categorized as a warming impact. And you see here that in the northern mid latitudes, let's focus on that, these areas with no impact make up to 80%. The ambiguous part is make up 12%, and this is really that one where we do not know what the climate effect is. And only those cases where we definitely know that a warming climate impact will arise, they are on the order of 10%. So these numbers give us an idea of the distribution of these different cases between these various cloud types. Now, why is this all important? To look at these contrail cirrus, how they develop, and in which areas or in which environments they are forming. A major part, besides the fundamental interest in knowing the climate effects, comes from the current discussion on potential short-term mitigation strategies of the climate impact of aviation by routing aircraft around areas where these contrails form. So that means if you can redirect an aircraft from, instead of flying through regions where these contrails will evolve, send it around or above or below, then you can avoid the contrails and you reduce the climate impact. That is the basic idea of a lot of efforts actually ongoing. So these diversion strategies require intelligent route planning, which, however, need reliable forecasts of ice supersaturated regions. If you cannot forecast them, you cannot avoid them. Currently, the numerical weather forecast systems cannot provide the required accuracy. This is actually a very active research field. And to improve this, the forecast, the better observation of atmospheric humidity is really needed. And here IAGOS steps in as the only available regularly operating research or observational infrastructure for aircraft-based humidity observations. This is the area around this target. Now, what is the problem? You see here an animation, this provided by Brice Bergans from Airbus within the Ciconia project. It shows the air traffic from Europe to North America, and the red areas define from a forecast these regions where long-living contrails will form. So you see really the problem right away. There is no space to redirect the aircraft around these huge red regions. Or they have to take large deroutes, and that would, of course, create additional CO2 emissions. And this is the major concern in the current discussion. So just to give you a summary of what can happen with these various options is here by a comment from Keith Shine and David Lee. Let's start from the left. So if we have this rerouting, we have the case that on the original flight plan, the aircraft would be guided through a region where the persistent contrails may form. Another route is defined, so the aircraft has to take a bit of a longer way, which has a bit of a more higher CO2 emissions, but the contrail is avoided, so the net effect might be positive for the climate. This is the successful rerouting. If we have another case that the aircraft is rerouted because on the original route a contrail is expected, but meteorological conditions have changed so that the contrail would have not evolved, then this is a kind of a bad outcome because we would have additional CO2 emissions, but no saving of, so to say, climate impact by the avoided contrail. Even worse in this third case here, when the aircraft normally would fly through a region where a contrail would form, it's redirected, but now meteorology has changed, and even on the redirected route, a new contrail cirrus will form. Then we have both penalties, the additional CO2 and the additional climate effect of the forming contrail. And this all needs to be assessed to come up with reliable systems for this flight rerouting and flight planning. And our observations want to make a contribution to this development. The other point we need to take into account is that if you want to compare the climate effects of CO2 and the contrail cirrus, you have to have in mind that you speak about two systems which completely different timescales. So CO2, once emitted, stays in the air for many, many years. The contrail, the cirrus dissipates quickly. So you have a radiative forcing where the contrail cirrus dissipates within hours, and the CO2 is still in the building up phase because it's adding up to the background CO2 case. So we really compare two very different themes, and for that the common metric is still not available to evaluate contrail cirrus against CO2. However, in a very recent paper which appeared in April this year, a modeling study was presented where they investigated the so-called climate sensitivity, which is the increase in surface temperature in Kelvin per watts per meter square of radiative forcing from either the contrail cirrus or CO2. And the outcome was that the Earth system is less sensitive to a radiative forcing by the contrail compared to the radiative forcing by a CO2. So this also has to be taken into account when we counterbalance radiative forcing from additional CO2 emissions to radiative forcing coming from contrail cirrus. That is another important, let's say, ingredient we need to take into account. And for that, with our knowledge on or the data we provide now for the coverage of the clouds of the sky with these different types of clouds and the different expected potential climate impacts, we believe that we can add a quite important database to this whole discussion because, and this is now the takeaways, as Andron announced already, I had to be a bit quicker today because of other, let's say, circumstances. We start with this really the knowledge that that our observation-based knowledge on long-living contrails within cirrus clouds, how they develop, what are their properties, how do they interact with the pre-existing cirrus, and the resulting radiative effects is severely limited. So here we have really to put hard work into it, and we believe that our contribution of the quantification of the areas covered with visible cloud, subvisible cloud, and clear sky helps to define the topics for modeling work. And from that, we can provide to the community that long-lived contrails here over the north at mid-latitudes, they exist to about 90% in regions which are already covered by subvisible or visible cirrus. So it's really important to dig out the radiative impacts of contrail cirrus existing in pre-existing clouds. That is of high relevance. The cases where we have really a significant warming impact, that means when contrails form in subvisible cirrus and clear sky with the net warming associated with that, this makes up only 10% at cruise over the northern mid-latitude. So it's only a minor fraction of the air. By far, the biggest fraction are the areas where the contrails form inside clouds, and that needs to be taken into account. The radiative impact of contrail cirrus in pre-existing cirrus is, as I said, highly uncertain, and this type contributes 50% to all contrail cirrus cases. So we definitely need radiative transfer calculations specifically on that topic to help, let's say, reducing the gaps of knowledge. And finally, our results suggest that potential flight rerouting concepts, which are now discussed and developed, they need to consider cirrus cloud coverage in addition to ice supersaturation. Actually, they exclusively focus on the forecast of ice supersaturation, But it becomes even more complex when we add Cirrus forecast, because cloud forecast is minimum as complex as the forecast of ISSRs, but most, I think basically it is even associated with higher uncertainties on that. But I guess I would say our results really pointed to the point that we need to take the Cirrus cloud coverage into account to come up with reasonable solutions for this approach to reduce overall the global climate impact of aviation. And with that, I would like to thank you for your attention. If you want to learn more on Yagos, please visit our website here. And I want to take that opportunity to gratefully acknowledge the support of all the airlines which are flying our instruments. And these are currently, and I really want to name them because we are very grateful to them. It's Lufthansa, Air France, China Airlines operating out of Taipei, Hawaiian, Air Canada, Iberia, Discover, and Cathay Pacific. They all support us by carrying our instruments free of charge every day. A big thank you to them, and a thank you to you for your attention.